Justin Miller, F. College Physics here. We are going to continue onward. Now, still looking at some oscillations, but we're going to focus our attention on this. What is this, you may ask? What happens if I take this and I go like that? Say, oh, it's a pendulum. And that's right, that's what we want to start looking at, is pendula. So this we can kind of consider to be what's called a simple pendula, or simple pendulum. We have a point mass here, highly localized mass, and the mass of these strings attached are insignificant. So what we're going to just focus on is really that this mass here oscillates about some axis of rotation. So I have two strings, that's true, but really it's the straight line distance from here down to the mass. It oscillates back and forth. And we want to figure out some aspects of its motion, like, hypnotize. Is it periodic? It seems to be, doesn't it? Just repeating itself over and over. 1, 2, well, let's see about that. Can we consider this simple harmonic motion? Is really one of the fundamental questions here. And can we mathematically represent things like the period of the oscillation and such? So again, this is what we call a simple pendulum, and what we want to start with is just that. I'm going to take this out of the way. Start examining aspects of simple pendulum. Simple pendulum. Point mass. It swings back and forth. That was crazy, okay? Back and forth. About some fixed axis of rotation, we'll call it. So what we're going to do is we're going to go ahead and say, hey, we've got some fixed axis here. Axis of our rotation, and then we can take ourselves, oh, let's just do it like this. We can take ourselves some string or something of that nature that is to be considered massless. And then we'll put our little point mass here at the end. There's our mass. And what do we have regarding this? Well, we have that the string is a certain length, which identifies us, or can be identified as the radius at which this mass will swing back and forth. And that's what we've got. So we've got this distance here, r, like that, radius of rotation. Which is really the length of the string. I'm going to call it R right now. We can switch that out a little bit later. And then we've got ourselves the point mass here. And what we want to know is, why does this object swing back and forth? So you say, well, because you lifted it up and you let go of it, and it wants to go that way. I say, yeah, that's true. That's true. But why? I say, well, because of gravity, right? That if I were to just take this mass and stick it right here, directly below the axis of rotation, what would it do? It would just stay there. It wouldn't oscillate back and forth. It would just remain right there. That's an equilibrium position of the system. That's what the mass wants to be. But I displace it from its equilibrium position and I let go of it, and a component of the gravitational force is, well, responsible for it swinging towards that equilibrium position. But then its momentum carries it through and goes back the other way. And then it turns around, then it turns around, then it turns around, then it turns around. much like a simple harmonic oscillator, right? It's a little bit different, but it's this kind of restoring force due to the force of gravity. And we have this equilibrium position. So I'm just going to go ahead and say that this is equilibrium position of the system. And then we can start looking at, well, what's acting on this mass? So we're going to ignore any air resistance and stuff like that, any variation in the gravitational acceleration with respect to variation in altitude. We'll just note that that is minimally small, insignificant. And then we say, well, what forces are acting on this? Well, there's a contact force, right? It's contacting the string here. So if there's a force of tension, that's good. So that force of tension, put ourselves some T hat there. And then we've also got the force of gravity. Yeah, gravity is acting on it. Which way does gravity act? Yeah, straight down. Of course. That should be a little longer, but we'll just do this. F sub G hat. There we go. Any other forces? The answer is no. We already said that those are going to be the only forces acting on it. So, force of tension, that's not going to really be responsible for it swinging back and forth. It's transmitted across the road, or across the string. So it has to be a gravitational force, right? Well, what happens if we go ahead and we resolve this gravitational force into two components? A component that is aligned with the string and a component that is perpendicular to the string. That is a parallel and perpendicular component, or equivalently, a radial and a tangential component. So, I'm going to move this down a little bit because it's going to be in my way. We'll call that F sub G hat right there. And then we can go ahead and say, well, we've got ourselves this F sub G radial, and I could say GR, but I'm just going to say, hey, that's the radial component of the gravitational force. And then we've got another component. Still going to be in my way. That's okay. This component here. This is F hat sub G tangential. Why do we want to identify that? Well, because it's the tangential force acting at some radial distance away from the axis of rotation, which substantiates the torque. And the torque produces rotation, right? The net torque produces the angular acceleration of an object. This is what we've got going on here. So let's just examine it like this. So I'm going to take that little portion right there and kind of blow things up a little bit. We've got things identified, but we'll redraw this slightly. This, and now we should be able to see that this force of tension and this force of gravity, hey, they're in opposite directions, and if this mass isn't going that way or that way, parallel to the string, that those two forces have to cancel each other out. So I guess we can write that over here really quick. F sub G radial balance with T hat. So that's it. Again, they add up to be equal to 0. So that just leaves us with this tangential component to be able to investigate, because it's the bearing on producing a rotation. So I'm actually going to draw it right here. Tangential component of F sub G hat. There we go. And what else do we have? We've got some angles that we could start looking at. Got this angle here, some angle theta. Well, when we start looking at torque, right? We go back and think about torque. Torque is equal to the cross product between some radial vector and force vector. And it's only, again, the tangential component of the force with respect to the radial direction that substantiates any amount of torque. And that's what this is. This is the tangential component here of the gravitational force. What we got to figure out is how do we quantify that, right? So we could take this, once again, and note that the magnitude of the torque is RF times the sine of theta. And, well, in this case, the magnitude of the force is F sub g. R is going to be the length of the string, and theta is the angle that it makes relative to this. So this we call theta is equal to 0 degrees. That's where we're going to measure things from. Equilibrium is at 0 degrees. All right, so we have that the length of the string, let's use lowercase. L is the length of the string, and F sub g is the actual force that's acting. Like this. Acting on the mass there. We can go ahead and say, well, the torque due to gravity, the magnitude of the torque due to F sub g can be written as, well, again, this is the axis of rotation here. This r that we've written over here, the radial distance, is actually the length of the string. So we'll just go ahead and replace that length of the string. And then we got F sub g here. F sub g times the sine of theta, where theta is the angle between r and F sub g. So what is that angle? Well, r again is a vector that points, r hat I should say, is a vector that points from the axis of rotation to the point of application of the force, which we would just say, hey, this is a point mass, it's right here at the very center. So we've got this vector that points down this way. So the r hat direction is that way. All right? So what is the angle between r hat and F sub g hat? We have this. That's the angle between them. Well, if we look at this, straight down and along the string, we've already called this theta up here. That's the same angle right here. Okay. As this goes straight down, we have that the force of gravity is completely radial and there's no more torque. And that's why we again can substantiate that position as being the equilibrium position. That torque would be equal to 0 there. But anyways, what can we do with this? Well, we can note a couple of things now. With F sub g being equal to mg, we have that sigma tau hat in terms of its magnitude. The net torque, there's only one thing producing the torque, is equal to L mg times the sine of a theta. And what do we know about net torque? Well, the net torque acting produces the angular acceleration of the mass about its moment of inertia. Usually we put I alpha. Let's do it. I alpha. I is moment of inertia of the system. And alpha is the angular acceleration. The mass. All right, so working with magnitudes now and noting, hey, this alpha has some directionality that we can associate with clockwise versus counterclockwise swinging this way or this way, this way or this way, we can start to write something else. We have that net torque is equal to I alpha is equal to L mg times the sine of a theta. Very nice, very nice. So what we want to do with this is start to unravel it a bit and see if we can extract out how the angular displacement of the mass, theta, is the angular displacement relative to the equilibrium position, how that varies with respect to time. If we can figure that out, we can figure everything else out too. So let us go ahead and do that. Now there's something that we need to note here, and that is directionalities. So kind of left this out for right now, but really again, alpha has a direction, which we can substantiate with plus or minus for something in one plane. And theta has a direction too, or the angular displacement has, it can be plus on one side. If it's plus on this side, then it's minus on this side. So what do we have? Well, if theta is positive, we have that the angular acceleration will be in the opposite direction. This is what we have. This object always wants to accelerate back towards the equilibrium position. That's the direction of the tangential component of the force. So if it's on the positive side, we can say well, that's negative. If it's on the negative side, we could say the angular acceleration is positive. The main thing is that there is a sign difference between these two terms because of this, theta versus alpha. So we kind of resolve this down into just talking about magnitudes, but again, direction still has to be embedded within this. So the main point with this is really we have that negative I alpha is equal to L mg times the sine of a theta. All right, so we've got to sneak a negative sign in there because it's a restoring force. So always back towards the equilibrium position, just like we had with the simple harmonic oscillator, right? The restoring force in that case was negative kx, spring force, opposite direction of the displacement. Anyways, what do we have with this? Well, we can solve this out, right? We have that alpha can be written as negative L mg times the sine of theta divided by I. So we haven't really said anything about the moment of inertia of the system. What's the moment of inertia of a point mass? It depends on the mass, right? And it depends on its radial distance away from the axis of rotation. This is just one point mass, right? So we have I for a point mass, if you recall, is equal to m r squared. So in our particular case, r is equivalent to the length of the string. So we can write that the moment of inertia, I, this point mass is m times L squared, r is equal to L. So what happens when we go ahead and put that in here? Oh, some magic, right? So we put in our ml squared in here for I, and then we've got this. Alpha is equal to negative L mg times the sine of theta divided by ml squared. So one factor of L cancels out, and the mass cancels out as well, and we are left with alpha is equal to negative g sine theta divided by L. All right, there's the angular acceleration. What can we do with that? What we can do with that is say, what is angular acceleration? How do we define it? Oh, that's right. It is correlated with the rate of change of angular velocity, which is correlated with the rate of change of angular displacement. So we can write this as d squared theta dt squared, that is what alpha is equal to negative g divided by L times the sine of a theta. There we go. So we get this nice differential equation here. And there's some familiar notions here in that, well, if you think back with the mass spring system, what did we have? We had that d squared x dt squared was equal to negative k over m times x. Is that at the same form? It's pretty darn close, right? We've got a negative g over L. Well, here we had a negative k over m. The spring constant and the mass were important here. The gravitational acceleration and the length of the string are important. And then we've got this x. Well, in this particular case, we've got the sine of theta. And that's where there's some difference here. Because now we're looking not for a function x that we take two time derivatives of it and we get that function back with some negative constant. We are looking for a function theta that we take two time derivatives of it and we get not theta back, but the sine of theta back multiplied by a negative of a constant. That is subtly different. This expression here gave us simple harmonic motion. This expression here does not, because of how the relation of the rate of change of theta to theta itself. All right, so what does that mean? Well, first off, we just write this is not simple harmonic motion. But it can be really close. And the contingency is that, well, you've got to keep theta small. So this is where we get into some approximations. Truly, if we want to know theta as a function of time, we'd have to solve that differential equation. We'd ultimately have to do some series expansion of sine and get some first, second, third order, fourth order, fifth order approximations and go from there. But there's something nice that happens for small angles. So we'll go ahead and write a however. If theta is small, the sine of theta is approximately equal to theta. Theta is measured in radians. This is known as a small angle approximation for the sine of theta. So how small does it have to be? Well, there's a general rule that we kind of use. If theta is less than 10 degrees, approximation is okay. The reason I don't say good is because, well, as you get closer and closer to 10 degrees, the approximation gets less and less good. For really small angles like 1 degree, what do you have? You have a really good approximation. As you get closer to 10, it falls apart a little bit. And then once you get over 10, it starts rapidly diverging from this sort of approximation. So let us just do a little experiment with this, but check it out. Check it out. Maybe you haven't seen a small angle approximation. We're going to actually utilize it a few different times throughout this particular course. It comes in handy. But anyways, what do we have? Well, we've got that 1 degree is equal to, well, we got 360 degrees is equal to 2 pi radians, right? So 1 degree is going to be that divided by 2 pi divided by 360, which gives us pi over 180 radians. All right, so again, this is valid when theta is measured in radians. So we can sort of look at equivalences, right? 1 degree is equal to approximately here, how many radians? Pi divided by 180 gives us 0.0174533. There's some more figures, that's a rounded value, but there we go. Well, what's the sine of 1 degree, which would be equivalent to the sine of this in radians? My calculator is already in radians, so I'm just going to take the sine of that value and see what I get. So the sine of that is, sine of 1 degree is equal to 0.0174524. 4524. Those are pretty close, right? To 3 significant figures were good, to 4 significant figures were good, to 5 significant figures were actually, that's where we start to go off. Just a little tiny bit. Those two numbers are pretty darn close, right? Well, let's check like 5 degrees. 5 degrees is equal to 5 pi divided by 180. 5 degrees is equal to 0.0872665 radians. Sine of that is equal to 0.0871557. So are those exactly the same? No, they're pretty close though, but again, they're not exactly the same. Well, we've gone from 1 degree to 5 degrees. There's a transition from these being really close to a little bit greater divergence here. To 3 significant figures, however, we would still be getting the same 0.872 rounded. No, this would round to 3, 0.873. We'd still be pretty close though, right? Well, let's look at 10 degrees. 10 degrees would be just equal to 10 times this, which would be equal to 0.1745533 radians. And then the sine of 10 degrees, sine of gives us 0.17364 8. I'm starting to get a little bit greater difference between those two values, but they're still pretty close, right? What happens if we go ahead and checked out like 20 degrees, 30 degrees? 20 degrees is 25, oops, let's go 2 times that. 20 pi divided by 180 gives us 0.349065, and we have then sine of 20 degrees equal to sine of that 0.34202. I'll just leave it at that. Well, now that's getting pretty far off, right? And it actually gets really far off as you start getting closer and closer to 90 degrees. But that's it. That's it. So as long as we keep the angle small, we can live in the realms of the small angle approximation. So we'll say, hey, we're going to keep the maximum angular displacement, theta, being equal to 10 degrees or less. What can we do then? Obviously, this is already stretched that out a little bit too far, but got to be able to draw it. What do we get? Or the sine of theta being approximately equal to theta. we have? We can write that d squared theta dt squared is equal to negative g over L times theta. Well, look at this. If we can use that small angle approximation, we get something that's in the exact same form. We're looking for a function that we take 2 time derivatives of it, and we get that same function back with the negative of a constant out front. This will give us, gives us simple harmonic motion. Fantastic. So for small angles, we do have that the pendulum, simple pendulum, gives us simple harmonic motion, which the key ingredient, again, with simple harmonic motion is that there's the independence of the period with respect to the amplitude of the oscillations. So as long as we keep the amplitude of the oscillations, we'll say theta sub 0, close or under 10 degrees, we get that the period of the oscillations is approximately the same. There's actually some variation, but again, we're using the small angle approximation. So we're not really worried about writing out an expression that gives us the correlation here. What we are more concerned with is what is the period of a pendulum. And well, we should be able to note that we could write that negative g over L is equal to some omega squared, and we can get ourselves that d squared theta dt squared is equal to negative omega squared times theta, and from this we can get our theta of t is equal to some theta 0 times the sine, cosine, doesn't really matter which one, sine, we'll use the sine, we'll use cosine, cosine of omega t plus phi. Great, that's it. That expression there solves this out. That is simple harmonic motion. There's a phase constant there, so we've got that omega there, where omega is equal to the square root of g over L. All right, so what do we get out of this? Well, that's not negative there, sorry about that. That's what I was looking at. It's negative omega squared is g over L. All right, so what we can get out of this, we know the period of oscillations is going to be equal to 2 pi divided by omega, which now for our pendulum says that, hey, the period is equal to 2 pi times the square root of the inverse of, not the inverse, the square root of L over G. There we go. Got ourselves the period of the oscillations. What does it depend on? Depends on the length of the string. And yeah, the gravitational acceleration, which is just some constant. This is telling us that as the length of the string gets longer and longer, the period gets larger and larger. So let's see. And you'd also have period variations if we went from, say, like Earth to the Moon, to Mars, to Jupiter, but we'll stay on Earth here. So let's take a look really quick here. I can vary the length of this. Look at this. So I can have a really small radial distance. This, our R, if you will. And we could look at how this oscillates back and forth. 2, 3, 4, 5, 6, 7, 8. Great. Well, what happens if I make this a lot longer? Well, if it's longer, the period should be greater, which means that it should oscillate slower. 1, 2, 3, 4, 5, 6. Wow, look at that. It's truth. 1, 2, 3, 4. The longer it is, the slower it oscillates. The bigger the period of the oscillation. So that's what we want to be able to get. And that's indeed what we have gotten. So that's fantastic. This is for a simple pendulum. Well, you ever seen those big grandfather clocks, that big armature that swings back and forth? And you say, how is that keeping track of time? Well, it swings back and forth in a very periodic way, such that every swing is 1 second. 1, 2, 3. Anyways, that's what we've got. However, that pendula, on say a grandfather clock, is not a simple pendula. It's a little bit more complex. We call it a physical pendula. So, what do we have with that? Well, we can take ourselves some extended mass, such as this. We've got a whole mass here. We've got ourselves an axis of rotation fixed here on the stick, and hey, I can set it into oscillations. Great. Well, we already had an expression that correlated the object's moment of inertia with the angular acceleration, and we ultimately used that, right? We had that expression right there. Alpha is equal to negative LmG sine theta divided by the moment of inertia of the system. Well, the moment of inertia of this object right here depends on the spatial distribution of the mass relative to this axis of rotation right here. If we start changing the moment of inertia, what happens? Is there a consequence for that? And the answer is yes, definitely there is. Definitely there is. We have to rethink things a little bit. So, let's check this out. I'm going to change the mass of this overall, but I'm just adding some mass down here. And what I'm going to do is set this into some oscillations there. 1, 2, 3, 4, 5. All right. What happens if I change the location of these? I'm not changing the mass. I'm not changing where the axis of rotation is, but I am changing the moment of inertia of the object, right? We have the distribution of the mass is now different. Well, what happens to the period of the oscillations? 1, 2, 3, 1, 2, 3, 4, 5, 6, 7. Compared to, again, 1, 2, 3. When more of the mass is down further away from the axis of rotation, it oscillates slower than when the mass is near the axis of rotation. So we have a system in which the actual moment of inertia needs to be taken into consideration. It's not just the mass of the object and how long the object is, it's how the mass is distributed relative to the axis of rotation. And that's an important aspect. So it's good. And we can have all sorts of different shapes of things that are ultimately or can be physical pendula. I could take some big mass here, large mass here, little mass here, and what does it do? It oscillates back and forth. What do I want to be able to understand? I want to understand the oscillations. I want to know what is the period given the spatial distribution of this object relative to that being the axis of rotation. We can have something like this. We could have the axis of rotation some distance away from the center of the object, where the object is some cylinder or something. What does it do? It oscillates back and forth. We're looking at small oscillations here. Or I can have some weird shaped object. Well, this isn't really weird, but an odd shaped object. And then I could hinge it somewhere like, hey, that's a kind of a weird place to hinge it, right? Well, what happens if I set that into oscillations? It oscillates back and forth. That's what it does. So I got my fan on, messing me up. I can oscillate it from over here. Okay, fan. Anyways, there's all sorts of different places that I could oscillate something from. And depending on the spatial distribution of the mass relative to that spot, we're going to get different periods, or possibly get different periods. I could start taking this, attach it to this, and then have some weird object, I don't know, stick it on over here, oscillates, all sorts of stuff. This is what we want to do, is be able to look at this, and we've already done most of the work here. Because of that expression right there, that expression. I is just a constant, assuming that we're not changing the structure of the mass as it oscillates back and forth. So for the physical pendula, the same general thing. Physical pendula, we'll just say. Extended mass. Oscillating about some fixed point. And again, what do we have? Well, let's do something weird looking here. So I can take something like this, and then I can take some object, say like this. Doesn't matter, I can put the axis of rotation here, anywhere. I'm just going to say the axis of rotation is right there. And this object would have some moment of inertia relative to that point that theoretically we should be able to figure out in some way. And what else does this object have? Well, the object has a center of mass. So somewhere this object's center of mass is, and we'll just say, hey, what the center of mass be like right there? What do we have with that center of mass? That center of mass is some radial distance away from the axis of rotation. Radial distance from the axis of rotation to the center of mass. And what do we have? Well, the center of mass is nice for saying that's the spot where we could say that gravity acts on the mass. And that's good. So at that particular point right there, we could say we've got the gravitational force there, F sub g hat, and that resolves into some radial component and some tangential component. So for this, we could say tangential component of F sub g hat, and we've got the same sort of setup that we had here. Same sort of setup. We've got that this force of gravity acts at some angle with respect to the radial direction, which is still just going to be theta, which is still correlated with this theta. Theta. So we can look at ultimately the angular displacement of the center of mass relative to it being an equilibrium position, where it would just settle down into a stable spot. And gauge things like this. Again, this is the same sort of thing that we have here. And what do we get out of this? Let's come right here. We get, we've already gotten, we get in the end that we can write that alpha is equal to negative LMG, but not negative L. L is going to stay as R in this case. Negative RMG is the sine of theta divided by I. Again, because I alpha is equal to the radial distance times the force of gravity times the sine of the angle between them, and this is what we've got. Same sort of thing that we had before. And again, we have ourselves that d squared theta dt squared is then equal to negative RMG times the sine of theta divided by I. I depends on spatial distribution of the mass itself relative to the axis of rotation. If theta is less than 10 degrees, sine of theta is approximately theta. We can use that again, and then what do we get out of that? D squared theta dt squared is equal to negative rmg divided by I, the moment of inertia of the object. And with that, we could go ahead and figure out then, excuse me, getting there. We could go ahead and figure out then what is the period of the oscillations. Let's sum this up here quick, because we've already done most of the work here. Omega squared is then equal to Rmg divided by I. So the period of the oscillation will be approximately we've got ourselves the square root 2 pi times the square root, get messy here, t is equal to 2 pi divided by omega, 2 pi multiplied by I divided by Rmg. I is the total moment of inertia of the system. And then there's one more thing that we could do, is we could note a tricky, or I shouldn't say a tricky way, an easy way of determining what I is for some nice objects. Parallel axis theorem. The moment of inertia of an object is equal to the moment of inertia relative to the center of mass of the object plus mass of the object times d squared. It's often how it's written. Where d is the distance d is distance from the axis of rotation to the center of mass. Which is equivalent to our distance r. From the axis of rotation to the center of mass, we call it r. Generally they use d, but that's pretty much what we've got going on here. So I sub cm, yeah, we should write that. I sub cm is the moment of inertia relative to the center of mass. So say we've got ourselves like a cylinder, a hoop or solid cylinder or something, and we hinge it somewhere that's not the center of mass. Well, what's the moment of inertia of this object? It's the moment of inertia relative to its center plus this mr squared, the total mass of it multiplied by the radial distance from the axis of rotation to the center of mass itself. So if we said that it was a solid cylinder, moment of inertia relative to the center of mass of a solid cylinder is 1/2 mr squared. If we say, well, we're on the outer edge of that solid cylinder, such that we took something like this and said, we're going to have this oscillate here, and just pretend this is solid. Oscillate back and forth relative to being fixed on its outer edge. Well, we have that the radial distance from its center to its outer edge is equal to the radius of it. So we would have that the moment of inertia of it would be 1/2 mr squared plus mr squared, which would give us 3/2 mr squared. Different, but easy to get. Calculus-wise, solving that all out with a bunch of integrals gets to be really tedious at times. They're good calculus problems, but parallel axis theorem comes in really handy a lot of times. All right, I gotta leave it at that. And Whew. It's like that big death pendulum. Whew. That was it. That was a rough one. Not really. All right. Yeah, that's it. Have a good day. Time's a ticking.